My name is Gabriel. Thank you for being here. Well, I want to talk. My presentation today is about faults. I started programming a while ago. I found Scala. I fell in love with the functional part, and I really like it. And it reminds me when I started studying programming. I kind of try to solve everything with recursion, and then move imperative programming, and kind of learned that loops were better. But when I found functional programming, I found that I could use recursion again. I kind of lost. Yeah, now it looks a little better. So my idea is to tell a little about the phone. Not everything actually, just a disclaimer. The first thing is probably you could have invented a fault by yourselves. The idea is to try that. So let's start with something really simple. Let's sum all the elements of a list. Who many here are familiar with Haskell notation? That's good enough. Well, another functional language, Scala. A few Scala and Haskell. That's good. So, how you will go to create a function without using for, just the basic things of functional programming, pattern matching, recursion, how you will do the sum of the list. Yes.
You could say that if the list is empty, the sum is zero.
Yeah. So basically, if you're doing pattern matching, we have two cases, the empty list and the case with the head, of the beginning of the list and the rest. And in case of the sum, what we should put in the first case? Yeah, 0, 0. And in the second case?
X plus the sum of x's.
Exactly. That wasn't really much complicated. There's a whole book based on this, like the little schema is all these recursion schemes. So basically, for the empty list, 0 is our base case, and the sum is the head plus the result of the recursive call on the rest of the list. So far, so good. Now let's do. This is if somebody that doesn't know Haskell and knows Scala. This is how it looks in Scala. Pretty similar. It's almost the same with some different details, but. Well, Haskell the notation is good enough for what we're trying to do. Now we're trying to do the same thing, but making a string with all the content of the list. Again, we do the same with decomposing. In the two options of the pattern, we have the empty case and the case of the head of the list with the rest. Does anybody knows what to put in the first case?
Oh, do you want the square brackets in the...
No, just
Okay.
all the values mashed together in one string.
Empty string.
Yeah? The empty string. And then the second case is slightly more complicated, but...
It would be show x concatenated with the function called on x.
Yeah, exactly. I mean, the only complicated part is like show is a function. Most of the languages go automatically from anything to string, and Haskell is more principle in that, and you need to call the function show. But basically, just this gives together all the one big string with all the numbers inside. And we are going again through the same exercise, but now for something a little different. Let's prove a property. Let's check that one property, the whole list fulfills that property. Again, we have the case for the empty case, the empty list, or the case of the head and the rest of the list. Somebody wants to try this? Yeah?
True for the first.
Yeah. The first one is true always. The empty list fulfills all the properties you want to ask. And the second one?
P of x and all the P of x.
Yeah. I mean, it's the same scheme we were using. Just we need to check the element and do and the rest of the list. Okay. Complicated so far? We are kind of just playing around with recursion and pattern matching. So, how we did record? The important thing is how we did recursion here. We had for our function we have one definition for the empty case and one definition for the head and tail case. So the important thing here is we're doing recursion on the structure of the list, because how the list is defined is the empty list or a combination of head and rest of list. That is what we call structural recursion. But we did 3 functions, and the code, if you look at the code, is kind of the same code. So let's try to generalize that, do some refactoring. Right? Let's put it all together, and it's kind of the same. We have value for the empty case, the empty list, and functions that do something with the first element and call recursively the rest of the list. I'm doing some arrangement to make everything looks like a normal function, not in fixed, just prefix functions. So we can see a little better what's happening. And I basically just put colors here because we have a value for the empty case and a function that combines the value of the head with the result of the recursive call of the rest of the list. Basically, we are using the same structure, right? What do you think?
So we can also rearrange the recursive call at the beginning. Would that affect things?
Interesting. But we're going to explore that later. Because right now I want to keep this structure, because now we can kind of generalize that. This is Haskell. We can extract functions everywhere. Basically, this is a function that takes one element and a list. This is a single value. So we can generalize all this in one big function that takes even we can write it. Let's call recursion over the list. It takes a function and a single value, and for the empty list we took that single value, and for the case with the head and the rest of the list applies f to the head and the recursive call. And does anyone know this function? The thing is, if you look, it's not exactly the name, but this function exists in Haskell, and it's called fall right. Have you ever used fall right in Haskell? That kind of thing. I mean, basically we just invented fall right. We're going to let fall left to the side and not talk about that right now. We can see it later what it does. Following so far? Cool. Okay, so we try a couple of things, a couple of recursive functions. We added basically the same shape, and if we abstract that, we kind of invented our fall right. And in Haskell, if you see the signature in fall right is all that at the top, basically says there's one function that takes an element and the result of the, basically combines two elements, one type A and one type B. Type B will be the result of the function, combines in one type B, takes another B that will be the initial value, a list of A, and returns a B. That whole signature is the signature of fall right, and it's the same signature of the function we just created. Usually, I don't know, very informally, if you want to give it a different explanation, I'm fine with it. Basically, you have a function f that combines the elements, the accumulation, and initial value z. And starting with z, you traverse the list backwards, in this case, applying f, producing a single result. That's kind of, I don't know, very informal definition of fall right. The important thing is we are applying functions with the initial value, combine everything, and basically we end up with this. Suppose we don't evaluate immediately. Actually, Haskell, you end with that. And that's what you get with fall right. As a side note, this is sadly not tail recursive because after the recursion we want to apply the function, so we cannot do optimization. Something to be aware, but it doesn't matter for this talk. So this is fall right. But what about other data types? We can do the same exercise we did. Let's take, I don't know. Let's take a tree, our own definition of tree, that has, it's a binary tree with values on the leaves. And we have either a branch of two trees that merge two trees together, and a leaf that holds a value. And also, after we got that, with that exercise, we'll see what happens with either or maybe. They are not recursive types. But we can define a fall for that too. So, I'm going to maybe a little faster with this, but if that's our definition, again, we want the sum of all the elements of a tree. We do the same as we did for the list, right? If this is a tree of integers, what we should put in the first case? A. And in the second case? Yeah. Basically, is in the leaf, we already had the value, we just return the value. And in the case of the branch, we just sum the results of the recursive calls. Yeah, let's do the same with the string. It's also again very simple. We get in the leaf, we just call show to get the string value, and in the branch case, we just concatenate the two strings together. So these are the recursive functions. What will be the common recursion? If I have that's the definition of the tree, I give it the signature that matches what we already saw together. There's one function that combines two trees and gives a result, and another function that we apply to the list that gets one value from the list and return. And let's call the second value, the second function, let's call it G, and the first function that combines two branches called F. What should I put in the first line, in the recursive tree? Sure. Basically, that's why I put the underscore, really, because the only thing we can do on this side is just get the A and apply G. And in the second case, basically, if in the list case, we apply F to the head and the result of the recursive call. Here, basically, we take F and we just pass the two values are the result of the recursive call to the function. And that actually is the fault for trees. Again, what we are doing is we are doing recursion on the structure of the data type we are using. And we define basically our cases matches the structure. And if we put those two things together, maybe we can see something interesting. So, everybody's familiar with cons list, the standard. Well, cons list is the standard functional programming list. In Haskell that's the definition. Basically, that is an immutable list that appends at the beginning. Basically, the operation is prepend. You put elements at the beginning, and the list grows from the front. And this is how it looks. This is the list 1, 2, 3. This is the match the empty list. The list with the only element is 3 is const 3 nil. The list 2, 3 is like this, and the whole list 1, 2, 3 is all this. If we fold over that list, we kind of transform this into this. Do you see some similarities between these two things? It's kind of the same shape. We did the same with the trees. We have a tree that, in our case, let's say this is branch, leaf, tree. This is a tree. I should have drawn the tree, but it has one branch with the 3, and the other branch again has 2 branches with the 1 and the 2. And if we fold over that with our folding function, we get this. Again, kind of the same shape as the tree. And that's the thing. If you see, fold our list, it gives you something with the similar shape of the list, and fold of a tree, we give you a similar shape of the tree. And I think that's the important thing. Fold, and this is the early point of my talk, basically. A fold replaces the data type constructors with functions. Functions that have the same shape, the same, if you want, the same arity, and basically the same signature as the data type constructors. That's why fold over a tree gives you this, like the F replaces the branch, and the G replaces the leaf. And in the case of the list, the F replaces the cons, and the Z replaces the nil. And also, the F matches the definition because it takes the first type is the value of the elements of the list, and the second type is the result of evaluating the rest. So, knowing all that, what you would think will be default over maybe? Yeah.
If we have nothing, then we use the default value. Otherwise, we use the value inside the JSON.
Yeah.
But we need to combine the value inside the
Yeah.
JSON with the default value.
Actually, it's kind of, because basically the maybe is almost like a list with only one element or zero element. It's very similar, but it doesn't have recursion. And now, default of either, basically say, okay, we are replacing constructors with functions. Let's say we want to get the value c. So we need a function from A to C, and a function from B to C. One for the left case, one for the right case. And actually, those functions, we just, I was doing this, I just decided, okay, that will be the results of the faults for those structures. So I look into Haskell, and those functions are there. They're just not called fault. But in the first case, it's called maybe, and the second case is either. But if you see the signature, again, matches the constructors, and here too, takes one function, another function, takes an either, and another. So it was kind of, okay, we are in the right track.
Question about that.
Yeah.
So if we think of maybe as a one or zero element list,
Yeah.
let's say we were summing the elements of the list, but we chose 10 as the initial value.
Mm-hmm.
So then, if we were to sum the empty list with 10 as the initial value, we'd get 10 back. And let's say we sum the list with just had 42, then we get 10 plus 42 is 52. It seems like in this case we're not considering the initial values if we had adjust.
Yeah. No. Basically, because that's maybe a difference. Probably I had to write some reason a little more about that. But that's the interesting point. But because we are not doing really recursive calls. The initial value, there is no initial value. There's value for the nothing and value for the just. And I think that's a little better way to think about it, because the initial value is for the case of the list, just because the list always has the nil at the end. But really, fault is like, if you think about replacing data constructors, that makes a lot more sense than saying, okay, in this case, it will not happen because basically the just doesn't have a nothing inside. So, to go again from the same to the same point, a fault really transforms the input into something else, basically following the structure of the data type. And if you go into the theory, or if you go to, I don't know, a Haskell meeting, everybody talks about catamorphisms. Catamorphism is an abstraction, basically the category theory definition of the fault. It comes from the word kata, that means downward, or according to, I think it's mostly according to, because it follows the structure, but also some people recommend, okay, think of a catastrophe that collapses everything into one. And this is kind of a joke, but I say there is a truly marvelous category theory explanation for this, which this slide is too narrow to contain. But if you're not scared, I can try to explain, because I barely understand that. But it is catamorphism. Like, we are running this. It doesn't. I mean, to be honest, I barely grasped this. So don't worry if you don't understand. If you understand, you have my admiration. But basically, a fold in catamorphism, we generalize the concept of fold, and basically we are deconstructing the data structure with an F algebra for the underlying functor. That's a lot of in one phrase, but the thing is, the way we define the constructors of a data type, we can think of an algebra. We can think of every constructor can be combined because we have recursive types. If you see the list, we are combining const, and nil, or the tree, we're combining branch. So basically we are doing algebra with those data types. Because those data types are parameterized, there are functors. And because there are functors, I have something that is called an F algebra. And because we are saying, okay, fold replace constructors with functions in the algebra. So basically we're saying, well, all this is a complicated theoretical way of saying, okay, we take the const list, the const nil, and replace with ffz. The thing is, because we are in a, I think it's Cartesian closed category, and I can prove that the data type constructors are initial. This is the initial algebra, and that means that I can go from that data type constructor algebra to any other algebra. That means my combination of functions that give me the fold. That means that I can prove that what I did is correct, and that's why I'm not lying when I'm saying, okay, replacing constructors with functions. There's another thing we can do that is even more complex. If you saw the previous talk about algebra, I can describe all my data types with some combinators. In this case, let's say these are the combinators. There's the product to put things together, the coproduct or sum to put alternatives. I represent the identity. That means the recursive call of the type constant is to hold a value, and 1 is the unit, the empty nothing value in the case nil. Maybe you can do it later. Basically, but with this I can describe the trees, I can describe the list, I can describe most regular data types. And now I have one thing that describes all my data types. And if I define a fold for this, these are the constructors of my data types, and my data types define all my program. I have one single fold that works for any data type. That means I can have only one definition of my sum function that will work on trees, on lists, on maybes, on either. But it takes a lot to explain the theoretical machinery. But it's something really interesting to see it working. It's still kind of something in progress around. So, I mean, all of this, what I wanted to say is, the fold is originated by the unique homomorphism that exists between the initial algebra and any other algebra. So, what's the problem? That's basically all I have to say. I mean, if you have questions, suggestions, whatever, we can go back to the point if you want. Thank you.